In the Diels Alder reactions, we need to remember that the reaction is stereospecific. And we had said before that if you start, for example, with this is your diene, this is your dienophile, and this is in cis conformation, this is the cis conformation of the diene, but you will have that the reaction is stereospecific, and your product will have them, these two groups, to the same size. Notice that you're making, let's say, like a cyclohexene, you will have that. If you start now with, say, another type of dienophile, if you did that, then your product will have, again, same cyclic, say, movement of electrons in your transition state. But now you will have these two groups need to be pointing to different sides. So we will put that one wedge and one dash to say that. Remember that we're changing the hybridization here from sp2 to sp3 in each of the carbon. Now, this type of reactions can also happen with an alkyne here instead of an alkene. So let me draw another example here. You say that you had butadiene, same as we did before. This time I'm going to put an alkyne here. And we want to have typically electron withdrawing groups. And I'm going to add, say, an ester on that side. In the dienophile, this reaction proceeds faster when we have electron withdrawing groups in the dienophile. That's your dienophile. But what we're doing when we have an alkyne is still we're using 2 electrons in the dienophile. So 4 pi electrons here into from the dienophile. So still you're doing this. You know, your product, you're using only 2 of the electrons in pi bonds, and so you're still going to have another pi bond on that side. So the product will have this. And you will have now, this is, you no longer using here wedge and dashes. Remember that now this is sp2 hybridized. There was sp here, sp2, sp here, and went to sp2. And so you will have the 2 ester groups. So we use a variety of electron withdrawing groups, can be aldehyde, ketone, esters, all of that. And the reaction works more effectively. Another thing besides what we have talked is stereospecificity. Specificity of the reaction. And again, that refers to if you start with the trans here, you get the trans here, or the cis, you get the cis. And another thing is when you have, I'm going to use a different dienophile. This time, a different diene, let's say. And this time I'm going to be using 1 dicyclopentadiene, which is locked in the cis conformation. So if I do that and say that I'm having this diene, now the reaction happens involving still 4 plus 2. So we're going to do this moving again in cyclic fashion. But what I want you to see is that this carbon right here is not participating. So we're going to draw the product in a couple of ways. So first, I'm going to do it, say, keeping this planar similar to that. So I'm going to form, say, similar to the drawing that I have on the right-hand side. I'm going to have like a cyclohexene, and I'm going to have these 2 cysteine twins. This is C's. I'm going to have those like wedges. But now I have an extra carbon that we didn't use. So what we're going to do is draw that as a bridge. So what we're saying here is that that is this carbon and did not participate. There is another way of drawing this, and it is in perspective. Now I'm going to do that type of drawing. Removing this one here, and this. And I'm going to draw now the, say, the cyclohexene in a different way. I'm going to draw 6 carbons this way. And that is that double bond. And now that bridge, I'm going to draw up here. And that is a bicyclic structure. And these are my bridge head, which I had here. All I need now is the metal groups. So now, when we have that type of drawing, we will have, say, positions here pointing downwards or inwards. So I'm going to draw 2 possible products. These two need to be on the same side. Say that I do this, or I'm going to draw similar bicyclic structure. But now I could have, again, pointing to the same side, since we started here with the cis. I need to keep that. So these are 2 possible products. Now, this one, with the 2, say, substituent pointing opposite to this bridge, we're going to call the endo product. And that is the favor product under, say, kinetic control, so which is most conditions that we use to favor the cycloaddition. So, and this is the exo. So we can also say that exo, these 2 are pointing to a small group, or we can also say that these 2 in the endo are pointing to, say, the large part of the bicyclic structure. Either way, I like to think that these 2 are opposite to that. Anyways, we need to remember then when we do stereospecificity that if you're forming a bicyclic structure, then the preferred product is the endo product when you will have that. That happens when you have these 2 C's. If you didn't have the C's here, but you have trans, then you will have 1 up, 1 down. It's not the case. But in this particular example, we have the 2 substituents of the same size. So started with the C's. We did this drawing like flat, and then this is the perspective. That's your bridge. And you need to keep these 2 substituents still to the same side. But the preferred product then is the endo, which is this 2 pointing away from that carbon.